Section 15.2, line integrals. So what we're going to be doing in this section is we are going to be integrating along some curve C in space. Okay, so we're given some curve C in space, and we're going to integrate along that curve. Now, the idea is we're going to come up with some parameterization, some piecewise smooth curve. We're going to talk about that. We'll get a parameterization for this curve that's going to take us from point A to point B by following along this path that we create, this curve that we create. And we're going to find our integral over that path. Okay, so let's begin by understanding what we mean when we say piecewise smooth curve. So smooth just means there's no cusps, there's no sharp edges. That's what smooth means. Piecewise smooth means that there are a finite number of smooth connected curves. Okay, so piecewise smooth is going to be a curve that can be split up into a finite number of smooth curves, meaning with no sharp edges, no cusps. So basically, in other words, they're differentiable on these individual pieces. So for example, this is a smooth curve, no cusps, right? That's smooth. Piecewise smooth, so PW for piecewise. Piecewise smooth curve means that it's got some smooth stuff, and then it might have some weird points, but it's got a finite number of those, right? Ooh, that's not even a function. Let's try again. But it's got a finite number of those, okay? So each one of these pieces, from here to here, that's a smooth piece. From here to here, that's a smooth piece. From here to here, another smooth piece. From here to here, another smooth piece. So it's a finite number of connected smooth curves, and all of these together are creating a curve C. This is going to be the path of integration. This is going to be our line that we're integrating over, okay? So path of integration. And what our job is going to be is to find a piecewise smooth parameterization for this curve that will take us from point A to point B to point C to point D to point E, right? It's just going to carry us along this curve. And it just occurred to me that what I just drew there makes it look like we're going another path. We're not. We're following this path. It's just going to take us through here, just like this. Okay, it's going to carry us just like this. So we've got to find a way to get from point to point to point to point. That's what we're going to do. So we will find a piecewise smooth parameterization, that's the word I'm looking for, parameterization, to follow curve C from beginning point to end point. Okay, that's what we are going to do. Now that's assuming it has a beginning and an end. It could be, you know, from negative infinity to positive infinity, however it's set up. But that's our job. That's what we are going to do. All right, so let's begin with an example here so we can see a parameterization of a piecewise smooth curve. So example. Okay, in this example, here's my z-axis, here's my y-axis. I'm giving us a little bit more perspective, so it's easier, I think, to see kind of what's going on. That is not z, that is x. Okay, so here's my curve. This is what I want to do. I want to travel from, I'll do this in purple, the point 0, 0, 0 to the point, let me make this a little bit thicker so it's easier to see the line I'm drawing, to the point 0, 2, 0, to the point 1, 2, 0, and then finally to the point 1, 2, 1. Now I realize my z scale is a little bit higher, but I wanted to be able to see this better. Okay, so this is the path that we're following. We're following along in this direction here. Okay. Now, this is not a smooth curve, clearly. I've got cusps here. Let me grab another color. I've got a cusp here and here. So this is not a smooth curve. But if I break it up into three pieces, where I have my first piece here, my first part of the curve, we'll call that C1. The second part being this piece, so C2, and the third part being the vertical piece here, C3. Then I have a piecewise smooth curve, C. Okay, so our job is to parameterize each part of this curve. So let's see if we can figure out how to do that. For C1, we are beginning at 0, 0, 0 and going to 0, 2, 0. So I need to figure out a way to get there. Well, we begin at the origin and we move only in the y direction. So really, oh, and I forgot to mention, we're going to be using vector valued functions to do these to define these curves. Okay, so I'm looking for some vector that's going to take me from the point 0, 0, 0 to the point 0, 2, 0 parameterized from t. So if I were to set this up and say, well, you know what if I just said, well, let's have our first curve be defined as t in the j direction. Okay, well, it goes from 0 to 2. So then I could say, well, t is between 0 and 2. Okay, that would work, right? Because that would begin us at 0, 0, 0, and then as t increased towards 2, it would just carry us along the y-axis until we reach the point 0, 2, 0. So that works. That works. So now let's take a look at the next piece, C2. C2 begins at the y component 2, okay? So our initial point is going to need to be 0, 2, 0. So we need to have something, oh, and then where we're going out to 1, 2, 0. So the y component here is constant. So whatever we come up with, we know we're going to have a constant y component. Now the z component is still not changing on this piece, so we won't have a k component, but we will have a j component. I'm sorry, an I component, because we are now moving in the x direction. So we're moving in the x direction from 0 to 1. Okay, so we need this to go from 0 to 1. But what can we put there? Well, if we end the last piece at 2, this is bothering me, I need to correct that. If we end the last piece at t equal to 2, we have to begin the next piece at t equal to 2. So t is going to begin at 2, and then it'll end somewhere else, and we'll figure out where that is. But the idea is we've got to go from 0 to 1. Okay, so maybe we could set this up as t minus 2. Would that work? Let me put this in another color because this is a question mark. Would t minus 2 work? Well, let's see. If I begin t at 2, I put in 2, minus 2 is 0, so I'd have 0 in the I direction. That works for our first point here. I need x to be 0. Now, if I put in another number, I need to end up when x is equal to 1. So it looks like if I were to stop at 3, that's exactly where we would go. So if I've got t minus 2 in the I direction plus 2 in the j direction, when t is 2, I get 0i, 2j, 0k, so that's the point 0, 2, 0. If t is 3, I get 1i plus 2j plus 0k, which takes us to the point 1, 2, 0. So it looks like this is going to work out very well for this one. So we've got t minus 2 in the I direction plus 2j for 2 less than or equal to t less than or equal to 3. So finally, our last component, C3, that's going to move us in the vertical direction, and we're going to keep x and y constant here. So we've got x equal to 1, so that's going to be 1i, plus y is equal to 2, so that's going to be 2j, plus now we need something for this, for z, that's going to take us from 0 to 1. So we got to go from 0 to 1. But this time our t is beginning at 3. Now because we're only moving 1 unit, my guess is that we can go ahead and end this at 4. We could probably come up with something that would work for that. So I wrote this a little too close. Let me move this out. I need a little more space. So for t between like 3 and I'm going to say 4. It's my guess. Because we're only moving 1 unit, I bet we can come up with something linear to take us up 1 unit. Okay, so we begin at 0. So I'm going to need something that's going to give us 0. So I'm thinking 3 minus t. Okay? So if I plug in a t here, I get, if I plug in t equal to 3, I get 0k. That's perfect. But look what happens when I plug in 4. If I plug in 4, I get 3 minus t is negative 1k. That's not what I want. I need positive 1k. So this doesn't work. So I'm going to get a nice red line here and say, nope, that does not work. So how can I fix it? Well, let's reverse the roles of t and 3. Now that may have been completely obvious to you. It's exactly what we did in the previous piece, but I wanted to throw it out there because sometimes you come up with something that works at one end but doesn't work at the other end. Sometimes you get an expression that takes you from the back end to the front end, like it would take us from 1, 2, 1 down to 1, 2, 0. Got to make sure we're following our curve from point to point to point. Okay. All right. So just a word of warning there. Okay. So instead, let's try I plus 2j plus t minus 3k for 3 less than or equal to t less than or equal to 4. Okay, so now if I plug in 3, I get 0k, so that's good. And then when I plug in 4, I get 1k, which is exactly what we want. So this is going to be our third component. So altogether, we have r of t is equal to the piecewise function t, oops, can't write tonight, t in the j direction for t between 0 and 2. We've got t minus 2 in the I direction, plus 2 in the j direction for t between 2 and 3. And finally, we've got, let me make my curly bracket a little bit bigger. For our third piece, we've got I plus 2j plus t minus 3 in the k direction, and that's for t between 3 and 4. Okay, and there's a piecewise smooth parameterization of our function. Okay, so we found a piecewise smooth parameterization of this curve. I probably should have written the instructions here, what we were doing. So find a piecewise smooth parameterization for that guy. That's what we were doing. That's all we were doing. So we found a parameterization that took us from point 0, 0, 0 to 0, 2, 0 to 1, 2, 0 up to 1, 2, 1. And that's exactly what we needed. And that's what we found. So there's our piecewise smooth parameterization. Okay, and why do we need this? We need this so that we can perform our line integrals. So let me go ahead and give you the definition of the line integral just right out of the gate here. So definition of the line integral. All right, so that definition is for f defined on a region containing a smooth curve, containing a smooth curve C. The line integral of f along C is given by this. So the integral of f of x, y ds is equal to the limit as delta goes to 0 of the sum from I equals 1 to n of f of x sub I, y sub I, delta s sub I. Okay, so there it is, the definition. Now this is in the plane. It does extend to three-dimensional space in exactly the same way. I'm not going to bother to give it to you because you're not going to use that to find the integral. So let me tell you how to actually evaluate the integral. So this is a theorem from our book. So how to evaluate these. So theorem, evaluating the line integral. Okay. If we have f is continuous on a region containing a smooth curve C, if C is given by a vector valued function r of t equal to x of t in the I direction plus y of t in the j direction, where t is in the interval from a to b. Okay. Then the integral over c of f of x y ds is equal to the integral from a to b of f of x of t, y of t, times the square root of the magnitude of r of t. So that's going to be, I'm sorry, r prime of t. So x prime of t quantity squared plus y prime of t quantity squared dt. Okay, and this does extend into three dimensions. So if we have c equal to r of t equal to x of t I plus y of t j plus z of tk, then we just have the integral of over c of f of x y z ds is equal to the integral from a to b of f of x of t, y of t, z of t times the magnitude of the derivative, square root of x prime of t squared plus y prime of t squared plus z prime of t squared ds. Okay? All right, so it does translate into 3 dimensions just like everything else that we've been working with. So this is our line integrals. This is how we're going to calculate them, and this is why it's so important that we are able to parameterize these curves in space, because we need to be able to use this in this way. Now, if the line integral is parameterized by the arc length, that's really nice. Let's do that. Let's just write this down. If C is parameterized, oh heavens to Betsy. You know what? Gooey. Try that again. Parameterized, close enough, by arc length S. Okay, just like we saw before, we get some pretty nice stuff. So our integral of 1 ds is equal to the integral from a to b of the magnitude of r prime of t dt, and that is equal to the length of the curve. Okay, so that's pretty handy, and sometimes we will be able to use that. So let's go ahead and do an example of a line integral. All right, so let's evaluate. Stop it. Evaluate the integral over c of x squared minus y plus 3z ds. Okay, where c is equal to the vector 1, 2, 1, and t is between 0 and 1. Okay, so the first thing we're going to need is we're going to need a parameterization in t, right? Okay, so c is 1, 2, 1, so that's not too bad. It's just a vector that's going out to 1, 2, 1. So we come out 1, down x2 or out x2, and then up 1. So it's this vector right here. It's difficult to see things and draw them. See, okay. So it's difficult to see these things sometimes, but that's it. Now, that's not too bad. This is taking us to the point 1, 2, 1, right? So just like before, we're going to need r of t equal to, now this is just a single smooth curve, so this will be very easy for us to come up with. In the I direction, we can go, oh, back this train up, guys. I'm sorry, I jumped ahead of myself just a little bit. What's the path that we're taking? What's the path that we're taking? We are going from 0, 0, 0 to 1, 2, 1. That's the path we're taking. That's our curve C. That's our line that we're following. Okay, so we need r of t such that it is going to carry us from 0, 0, 0 to 1, 2, 0. Okay, so we've got to be cognizant of where we're starting and where we're stopping. So that was my mistake not mentioning that to you just a moment ago. So I wanted to make sure I did that before we went any further. Because what we have to do is when t is 0, we have to be at 0, 0, 0. So that's easy enough if I just have t, 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 right? Plug in a 0, you get 0, 0, 0. No problem. But when I plug in t equal to 1, I've got to wind up at the point 1, 2, 1. Well, if I plug in t is equal to 1 for the x component, I get 1. For the y component, I would get 1 again, but I don't need 1, I need 2. So let's multiply that by 2. And then for the z component, I need 1 again, so that works. So let's double check. If t is 0, I get 0, 0, 0. Check. If t is 1, I get 1, 2, 1. Check. So this is our parameterization r of t. This is what we needed to find. Okay. This one was extremely straightforward. There are some, of course, that will be more challenging than this. But just to give you an idea of what we have to do, this is what we're doing. Okay. Okay, so we have r of t, we have our path now, our parameterized path, and we have our original function here, right? So this is what we are going to have to figure out. What is this? Well, let's see here. Our integral is going to be from t equals 0 to 1 of f of x of t, y of t, z of t, times the magnitude of r prime. You know what? I don't need a square root if I'm going to write it as the magnitude. The magnitude of r prime of t, okay, dt. Okay, so, well, what is f of x of t, y of t, z of t? We need to know this. So x is equal to t. This is x of t here. Grab another color, green. So this is our x of t, this is our y of t, and this is our z of t. Okay, so we are going to plug these into our function. So x of t is t, so I'm going to replace x with t, I'm going to replace y with 2t, and I'm going to replace z with t. So f of x, go back to main color, f of x of t, y of t, z of t, that is going to be equal to t squared minus y is 2t plus 3 times t. Okay, so this is going to be t squared plus 1t. Okay, now we need r prime, the magnitude of r prime of t. So the magnitude of r prime of t, that's going to be equal to the square root of 1 squared plus 2 squared plus 1 squared. So that's the square root of 4, 5, 6. Okay, so now we have it. So this integral is the integral from 0 to 1 of t squared plus t times the square root of 6, with respect to t, integrated with respect to t. Goodness, words, English, what is this? Okay. All right, so this is the square root of 6 times the integral from 0 to 1 of t squared plus t dt, very straightforward integration. So this is the square root of 6 times 1/3 t cubed plus 1/2 t squared, evaluated from 0 to 1. Plugging in a 1, I'm going to get the square root of 6 times 1/3 plus 1/2 minus, plugging in a 0, we just get 0. So this is going to be square root of 6 times 5/6. So this is going to be root 5 over root 6, or if you prefer it rationalized in the denominator, 5 root 6 over 6. Okay, so there was our integral over that curve C. So that's basically the process all the way through. Now, of course, finding r of t can be much more challenging than that, but we can always find something. We can usually find something to represent these curves. Sometimes they give us the parameterization they want us to use. Parameterizations are not unique, right? But here's something interesting. If you are integrating within a conservative vector field, that integral is independent of path. And that's actually something we'll see in the next section. But just a preview of coming events, the path does not matter if we are in a conservative vector field. We could take the easiest possible path from point A to point B, and we'll be good to go. Okay, but we'll see more of that in a little while. Okay, so let's see another example here. Okay, so suppose we are given a path in xy that takes us from the point 0, 0 to the point 1, 1. I'll make this big so we can see it. Okay. And then follows y equal to x squared back down here. So this is y equal to x, this is y equal to x squared. Okay, so there's our path. We are going up to the point 1, 1 and then back down to 0, 0. Use a brighter color. The purple doesn't show up very well against this dark background. There we go. Okay, so this is our path that we're taking, and we are going to evaluate the line integral of x ds. And you know it's a line integral because it's integrated over c, a curve, a single curve. So this is a line integral of x ds. Okay, so let's get this thing parameterized. So we're going to need to figure out how we're going to get from 0, 0 to 1, 1 along y equal x and then back again. All right, the fact that it's telling us the equations to get there mean we're in pretty good shape here. For the first curve, I'm gonna call these C1 and C2. Okay. For C1, it's pretty straightforward. We let x equal to t, then y is equal to t, and bam, we have a beautiful parameterization, right? So that's going from 0 to 1. So for t, from 0 to 1. All right, then r of t is equal to t for t between 0 and 1. So I'll call that R1. Okay, for the second curve, let's make this another color just for fun. So for C2, this one we've got y equal to x squared. So again, if I let x equal to t and y equal to t squared, that would be a good parameterization. The problem is that's not actually going to work for us because I've got to now go from 1, 1 down to 0, 0, and I can't let t be 0 to 1 because I've already used t equal to 0, t between 0 and 1. So this parameterization that I have listed here is actually not going to work for us. So this isn't going to work because it won't get us where we need to be from point to point. Okay, so whatever we come up with, we have to begin at 1, 1. We have to end at 0, 0, and t has to be between 1 and something. Maybe 2. My guess is that would work, but I don't know. So let's see if we can come up with something. So if t is 2, I need to be at the point 1, 1, and I'm going to need to incorporate this idea that y is equal to x squared. So let's see here. Let's start with t. I need to be at 1. Well, if I'm going to start at 1, that would work, except I need to be, like I can't just say, oh, well, let x equal to 1, because x isn't constant at 1. So what if I said, well, what if x was equal to 2 minus t? Would that work? Would that give us the point 1, 1? Would that give me x equal to 1? And the answer is yes, it would. But then y is dictated to be x squared, so that would be 2 minus t squared. So that would be 4 minus 4t plus t squared. So if x is 1 here, if t is 1 here and I plug that in, do I still get 1? And the answer is yes. Yes, we do. Okay then, so now the question is, can I put in a 2 and get back to the point 0, 0? So this works for t equal to 1. If t is 1, we get 1, 1. Okay, so that works. So now let's see if I put in 2, if I get 0, 0. So if I put in a 2, I'm going to get at t equal to 2. We get x is 2 minus t, which is 2 minus 2, which is 0. So that's good. That's where we need to go. And then for the y, I'm going to get 4 minus 4 times 2 plus 2 squared. So that's going to be 4 minus 8 plus 4. Ooh, 4 minus 8 plus 4. That's 0. That works. So this parameterization will work. So I started it with x because y was a function of x. Started with x, got my parameterization, plugged that into y, checked my values at either end of my interval to see if it works. And it does work. So that's going to be our parameterization for C2. So let me go ahead and just write that over here underneath C1. So C2, we have x equal to 2 minus t. So y is equal to 2 minus t quantity squared. And that is for for t between 1 and 2. Okay, so then our 2 of t is going to be equal to 2 minus t in the x direction, 2 minus t squared in the y direction. And again, 1 is between 0 and 2. 1 is between 0 and 2. Good leave. T is between 1 and 2. Okay, so here are our parameterizations. Here and here. Okay. All right, so this does require a little bit of side work, but we got it. No big deal. Okay, so because we have to follow this curve from point A to point B to point C, right, or back to point A, if you will, we are going to have to set up two separate integrals. We're going to have to integrate over C1 and then C2. So our integral over C of x ds is going to be our integral over C1 of x ds plus our integral over C2 of x ds. So this is following the same properties that all of our integrals have followed all this time. So we need to get these things set up. Okay, so remember, for the first one, we are going from t equals 0 to 1. For the second one, we are going from t equals 1 to 2. Okay, so our function is x. So for the first one, x of t is 2 minus t. So that's our function value right there, 2 minus t. And ds is just the magnitude of r prime dr, or dt, right? It's just the magnitude of r prime dt. I should probably write that down. That's kind of a big deal. Let's do that. So let's keep in mind, I'm just gonna jot over here to the right. Sorry, I know, I'm getting motion sickness. So just something to keep in mind, ds, I lost my train of thought. It's hard to talk and think and write at the same time. ds is equal to the magnitude of r prime of t dt. So that's equal to the square root of x prime of t squared plus y prime of t squared, and if there's a z component, z prime of t squared dt. Okay, so just keep this in your wheelhouse. You're going to need that. That's just the translation here. So I've given you that in previous videos for dA and things like that. So I wanted to make sure we did it here as well. All right, coming back. Okay, there we go. Okay, we'll get that out of the screen. There we go. Okay, so just x is 2 minus t, so that's our x of t, and then the magnitude of r1, or r prime of 1. So let's come back up here. What is r prime of 1? Okay, that's going to be equal to 1, 1. So that's the magnitude of 1 squared plus 1 squared dt. Okay, now we're going to do the same thing for the second part of our curve. So x for our second parameterization is 2 minus t. So that's 2 minus t. Oh, dear me. Just realized that I screwed up the first one. For r1, x is equal to t. That's it. X is equal to t. So please make this correction right here. I do apologize. So x is equal to t. Whew. Okay, better. Now, for r2, that's when x was equal to 2 minus t, and we need the magnitude. So I'm going to need r prime for the second function here. So r2 prime of t, that's going to be equal to negative 1 and 2 times 2 minus t, chain on negative 1. Okay, so that is negative 1, negative 4 plus 2t. There we go. Okay, so we're going to square those. So negative 1 squared plus 2t minus 4 squared dt. Okay, so let's see what we get here when we try to evaluate these integrals. Okay, so our first one is from 0 to 1 of t times the square root of t dt. Our second one is the integral from 1 to 2 of 2 minus t times. Okay, let's see, what do we get here? We've got 1 plus 2t minus 4 quantity squared dt, but I'd like to take that 2 out. So that's going to be 1 to 2 times 2 minus t, square root of 1 plus 2 squared would be 4 times t minus 2 quantity squared dt. All right, so the first integral is really very simple. This is going to be root 2 over 2t evaluated from 0 to 1. And let's see if we can find a way to integrate this second integral here. Okay, so I think what I'm going to do is the first thing I want is to let u, I'm going to do a u sub, let u equal to t minus 2. Then du is equal to dt, so this will be a very straightforward sub. 2 minus t is negative u, so this is going to be plus the integral of negative u times the square root of 1 plus 4u squared du. And this one would be then integrated from 1 minus 2 is negative 1, and 2 minus 2 would be 0. Okay. And then let's see, can we figure out a way to integrate this? Yes, we could do another u sub, but not u, I've already got u here. So let's do a v sub or something. So I'm going to now let, oops, I tried to change colors and failed. Let v be equal to 1 plus 4u squared, then dv is equal to 8u du. So 1/8 dv is equal to u du. Okay, so then my u du gets replaced with 1/8 dv. So this would be the integral from, it's not going to be negative 1 anymore, right? So let's see here. If I put in negative 1 for u, I get 1 plus 4 is 5. If I put in 0, I get 1 of negative 1/8 dv. So I'll put the dv at the end. Square root of v dv. Okay, so that's going to be the integral from positive 1/8, then we'll reverse the bounds of integration from 1 to 5, of the square root of v dv. So that's going to be equal to 1/8 times v to the 1/2. Integrate that, we get 2/3 v to the 3/2, evaluated from 1 to 5. So that is 1/8. 1/8 times 2/3 would be 1/12, wouldn't it? Let's go ahead and do that now. 1/12, and that's going to be 5 to the 3/2 minus 1 to the 3/2 is just 1. Okay, so let's come back over here and see what we've got. So I didn't finish evaluating this first part of the integral, did I? So this is going to be root 2 over 2t. At 1 is root 2 over 2. And then at 0 it's 0, so it's root 2 over 2. So altogether what we've got is square root of 2 over 2 plus 1/12 times 5 to the 3 halves minus 1. Ooh. There we go, keep my brackets consistent. So that's going to be root 2 over 2 minus 1/12 plus 5 to the 3 halves over 12. And then that's going to be 6 root 2 over 12 if I want to change to an LCD. So that's going to be 6 root 2 minus 1 over 12 plus 5 to the 3 halves. So we could do it this way. Anyway, but you get the idea, I hope. Now, that was a little bit of a challenging integral, but here's a question for you. I created a piecewise smooth curve, right? I created that piecewise smooth curve where t went from 0 to 1 on both of them. But is there any reason I could not have simply taken my curve, integrated over the first curve, let t be 0 to 1 there, and then gone back, integrated over my second curve, and let t be 0 to 1 again? And the answer is no. We're going to get the same answer no matter what. As long as our parameterization for t is going to take us from, the initial point to the terminal point of that piece of the curve, it's perfectly fine. We can be a little bit redundant with our t's if we want to. We want to make it easy for us to create, to integrate. Okay, so in this case, it worked out perfectly fine. We didn't have any difficulty at all, and I think you'll find that to be true in most cases. It should work out very nicely for you. But anyway, that's the line integral over our curve C for this particular function. All right, and if you have questions about that, do please let me know. Okay, so 2 more quick topics here. I don't want to spend too much time on them, but I do want to give you their definitions. So the line integral of a vector field is as follows. So if F, capital F, is a continuous vector field, defined on a smooth curve, C, given by R of t for t between, for t between a and b. Okay, so t is an element of the interval from a to b. The line integral of f on C is the integral over C of f dr equal to the integral over C of f dotted with t. Remember t, the unit tangent vector, integrated over the arc length of C. That is equal to the integral from a to b of f of x of t. Wow, damn, let's do this. X of t, y of t, z of t. Okay, dotted with r prime of t dt. Okay, so that's how that's going to be. This, of course, is the one we're going to be using primarily to do our evaluation. All of this is the definition. All right, so there's your function. We've got f of x of t, y of t, z of t, where these are, of course, going to be, we take our function f, we take whatever the corresponding component is in R, plug it in for that value, multiply that by R prime of t, or I'm sorry, dot it with R prime of t, and boom, we have our line integral over the vector field. Okay, one last thing I just want to share with you. We can also think of line integrals in differential form. I promise this video is going to end soon. Okay, so line integrals in differential form. This is just going to be, commonly used. It's really quite straightforward. We have our integral over C of f dotted with dr. Okay, that's going to be equal to our integral over C of f dotted dr dt. Okay, so that's going to be equal to our integral from a to b of m in the I direction plus n in the j direction, dotted with x prime of t in the I direction plus y prime of t in the j direction, dt. That is equal to the integral from a to b of m dx dt plus n dy dt, dt, which is just equal to the integral from a to b of m dx plus n dy. And there you go. So it can be very handy to think of it in this differential form. Pretty straightforward to evaluate that particular integral. Okay. You know what, I said it's pretty straightforward, and it is, but not if you don't really fully understand what you're looking at here. So we have our parameterization, right? We're going to have this parameterization r of t, and dx is going to be the derivative of that parameterization of x, right? Dx. So we're going to have, for example, what is dx and dy? Well, for example, if I have my parameterization with r of t to where I have x of t is equal to something like 3t squared, then dx is just equal to 6t, right? That's your dx, and same for dy. So that's what these are. I'm not integrating m with respect to x or n with respect to y. They're literally just the derivatives of those parameterized functions. Okay. So that's it for this one. As always, if you have questions about this, please let me know. Do try the homework, give it a shot, see how it goes. I think once you get into it, you'll see it's really not that daunting. So line integrals aren't as scary as they'd like to make you think they are. All right, y'all take care. Have a good one. If you have questions, let me know.